So today we're going to be discussing the fundamental theorem of calculus and how to evaluate it. Let's just go back to the beginning. So if I ask you to find the antiderivative, remember the antiderivative can also be called the indefinite integral. And this we did a few days ago, and we talked about how the fact we could take something, if we have a given function, when we take the antiderivative of it, or we work backwards from the derivative, we get the antiderivative, and we have to remember to do that little plus c. So moving back over here, our rule for finding the antiderivative is we add 1 to the power, divide by that number. So this would become x squared over 2 plus, and when I move on to the next term, if that's just a 1, we're just going to attach an x to it, plus c. Remember, we work backwards. So this would be what we call our antiderivative, okay? And, so far we have introduced the concept of the antiderivative, the definite integral, and the basic properties for the definite integral. Today we're going to try to connect these concepts and discuss the fundamental theorem of calculus. Now remember, the definite integral is now represented with the same sign, but now we have a lower bound and an upper bound, and this represents the area bounded by a curve and the x-axis on a given interval. AB. Oh, that's a terrible B. Sorry. That's even worse. AB. Okay. So we can also say the area under a curve or under f of x. So just be aware of the different ways that we can, write a problem. So we're going to now try to make the connection between these two things. So I'm going to ask you to sketch y equals t plus 1. Okay, this is the same as sketching y equals x plus 1. We're just using something we call a dummy variable. No big deal. So this would be t is our x-axis, and this is our y-axis. So if we want to sketch y equals x plus 1, that's going to be a line, a y-intercept of 1, and a slope of 1. So our line would be something like this. Does not have to be perfect. We're just using this as a visual aid. We can label our line. And remember, we can also write this as f of t equals t plus 1. So this would be f of t as well. So express the area from 0 to x as a definite integral. So basically, if I was expressing the area from 0 to 1, I would stop here. 2, I would stop there. I'm going to some arbitrary x value, so we'll just go there. I'll just pick some arbitrary x value. And if I was going to kind of shade this area, it would look something like that, 0 to x. So if I want to express this as a definite integral, now I'm going from 0 to some value x, t plus 1. Now this is going to be a little confusing, but since our variable is t, we have to write dt. And again, it's just a dummy variable. So this would be expressing the area from 0 to x as a definite integral. Now let's express the area as a function of x. Okay. So now this is a little bit different. Now we're going to go back to geometry. Okay. So if I want to express this area as a function of x, I look to see what shape I have here. I have a trapezoid. So my area formula is going to be h over 2, b1 plus b2. Now, just like we did previously, we're just going to go back into our picture. So I have area as a function of x is going to be, well, now my base, I don't have a number. So the base is whatever this length is. So the base, the height is h, which is x over 2. Base 1, base 2. Remember, that's how our trapezoids work. So base 1 is easy to see. That's just 1. And base 2, if you think about it, base 2 is just going to be whatever you get when you plug x into the given function. So that's x plus 1. Now if I simplify this a little bit, I get x over 2 times x plus 2. And just one more step we're going to distribute through. I get x squared over x squared over 2 plus 2x over 2 is just x. Now we're going to stop here for 1 second, and what do you notice? What do you notice about these two functions? It's not that easy to see because this is a t, but if we go back into the beginning, what do you notice about the antiderivative and the area function? They're the same thing. Okay. So our area function is really the antiderivative. Except there's no c. So we could actually write this area function as an integral from 0 to x of f of t, which is our given function dt. Okay, so here's the connection, and here's where we come up with what we call the fundamental theorem of calculus. So there's two pieces to the fundamental theorem of calculus. The first establishes a relationship between the derivative and the definite integral. And this looks like this. And all this means is the derivative of the antiderivative is the original function itself. Okay. Now, that's a kind of tough concept, so we're going to deal with that next year. Okay, we're going to go into a lot more depth next year. Today, my focus is just for you to be able to understand how to evaluate. So the fundamental theorem of calculus part 2 provides a method for evaluating a definite integral by hand. So whenever we see something, a to b now, if we have a definite integral, we're going to take the antiderivative and evaluate it from a to b. So this is our notation. And what we're going to do is we're going to plug in b, plug in a, and subtract those two values. Important here, rather than what we did with the Riemann sum, now we're going to get an exact area. Okay, so when we evaluate the definite integral, we're going to get an exact area. Our steps: find the antiderivative, plug in b, plug in a, and you're going to subtract those two values. Now, I just want to go back to this, why is there no c? Okay, we have to remember there's no c. So real quickly, and I want to also point out right now, there's a really huge math proof that shows you how this works, but we're not going to go into it. We're just going to, this is our method we're going to use. So why don't we have to worry about the c? Well, think about it. If you take the antiderivative and then you do what we say, if you plug in b, you'd have f of b plus c minus f of a plus c. When you distribute through, your c's are just going to cancel out, okay? So when we're finding just an antiderivative or an indefinite integral, we have to remember to add the c. But when we're evaluating a definite integral, we don't worry about the c. All right, so now here's the good part. Here's just the plain old math. We're just going to work through these problems and we'll be all set. Find the value of each definite integral. So I'm going to go back to my steps. I'm going to find the antiderivative. The antiderivative of this function, 2x squared over 2 is just x squared plus 3x, and I'm going to evaluate that from 0 to 2. So basically I'm going to take it, I'm going to plug in my 2 squared plus 3 times 2. This is my f of b minus f of a. So now I'm going to plug 0 in to the antiderivative. And then I'm just going to evaluate this. 2 squared is 4, 4 plus 6 is 10. This just is 0, so 10 minus 0 is 10. Okay, so that would be the number you get when you evaluate the definite integral. So let's just try a couple more, get a little bit more challenging. So I have 3x to the 1/2 minus 2 dx, and I'm evaluating this from 4 to 9. First, I have to find the antiderivative. 3/2 x to the, I'm going to add 1 and divide by the power. Divide by 3/2 means multiply by 2/3. Minus 2x, and that's going to be evaluated from 4 to 9. If you notice here, that's just going to cancel out. So I have x to the 3/2 minus 2x from 4 to 9. Remember, plug in the top number, plug in the bottom number, and subtract them. And now here, I know you guys want to run to your calculators, but you really have to know how to do the math. So let's set this up. 9 to the 3/2 minus 2 times 9. Okay, we want to plug it in to the function, just a substitution at first. Minus. When I plug 4 in, I get 4 to the 3/2 minus 2 times 4. F of b minus f of a. 9 to the 3/2. Rather than running to your calculator, again, remember, this is power over root. Square root of 9 is 3. 3 cubed is 27. 27 minus 18. Square root of 4 is 2. 2 cubed is 8. 8 minus 8. And once again, the math is not that difficult, and you need to be able to do this for next year. 27 minus 8 is 9. 9 minus 0 is just 9. Okay. Almost there, guys. So for number 3, and I know it's been a few days, so when you look at this, when you go to find the antiderivative, we have to think about, I don't have a rule for this, so I have to rewrite it. Leave this alone. Don't worry about that right now. Just worry about putting this into a form that you can deal with. X squared over x is x plus 5. So that simplifies to that. Now we're going to take the antiderivative. And I get x squared over 2 plus 5x. And we're going to evaluate this from -4 to 2. And remember, you don't have to worry about the c here, right? We don't ignore that back because they will cancel out anyway. When I plug in 2 squared over 2 plus 5 times 2. And notice I'm taking the time to physically plug in the number. Minus -4 squared over 2 plus 5 times -4. Sorry, it's squishy. So now I have 2 squared over 2. 4 over 2 is 2. 2 plus 10 is 12. -4 squared is 16, so this is 8 minus 20. 8 minus 20 is -12. 12 minus -12 is 24. Okay, so pretty easy stuff. Integral from 9 to 16, once again, think about it. This is really x to the 1/2 over x. So we're going to have to simplify this first. 9 to 16. X to the 1/2 over x is really x to the -1/2. So I'm going to be using my antiderivative rule. -1/2 plus 1 is 1/2. Divide by 1/2 is the same as multiplying by 2. And I'm going from 9 to 16. So I'm just going to f of b. Well, x to the 1/2 is really just square root of 16 times the square root of 9. 2 times the square root of 16 is 8. 2 times the square root of 9 is 3. So 8 minus 2 times 3, 8 minus 6. Our overall answer here is going to be 2. Now, just because we physically evaluated the definite integral, I kind of want to remind you, okay, whenever we evaluate a definite integral, we really are finding the area between the curve, whatever the given curve is, and the x-axis over a given interval. So here we want to work from scratch. I want to find the area between this curve, this is our parabola, from 0 to 3. So visually, when we're done evaluating our definite integral, our number represents the area under this curve, that shaded region. Okay. So we have to set this up. We have to set up the definite integral for this situation. So the area between, so my area is going to go from 0 to 3, and the function, the curve, is x squared minus 2x plus 1. Okay. So that's how we would represent this using calculus. Words, calculus. And now we're just going to use what we learned to evaluate this. So I take the antiderivative, oh, I like to work underneath. Take the antiderivative, x cubed over 3 minus 2x squared over 2 is just x squared, plus x from 0 to 3. And I know it looks scary and messy, but we're going to see very quickly how easy it is. F of b, 3 cubed over 3 minus 3 squared plus 3. There's my f of b. Now plug in the bottom number. F of a, 0 cubed over 3 minus 0 squared plus 0. You can see right away this is just going to become a 0. So we really just have to focus on that. And don't think this always becomes a 0. It just, happens to be in these couple examples I picked. So I have 27 over 3. That's going to be 9 minus 9 plus 3. The definite integral, or the area under the curve, is 3. And remember, this value is an exact value. Okay. It's not like the answer you get when you do a Riemann sum. Okay. So let's just kind of move down here. Guys, this is your last lesson. I'm so proud of all of you and the work you have put in these past few months. I hope everyone has a great summer. Stay safe and healthy. Please remember to keep these lessons and notes from limits on, okay, when we were still in school, as a resource for next year. You'll find them very, very helpful. And I can't wait to see you all again. Bye.